Okay. Starting in 3, 2, 1, go. Hi guys, this is Mr. Gilmore with the 1.1 Systems of Linear Equations. We're going to go ahead and get this year started off right. I want to make sure you guys are staying on task even though I am not there. And so I'm just going to do some quick recordings for our first couple lessons while for the days I'm not there. And so I just threw these PowerPoints together real quick to give you guys kind of something to see while I'm talking about our first lesson. One thing I need you guys to do though before you get started is to head over to Canvas and head to the Chapter 1 page and locate the 1.1 System of Linear Equations digital text file and open that up. I should say 1.1 DT. That way you guys have the textbook up in front of you as you guys are listening to this, and that way you guys can also kind of follow the text as I'm giving you guys some information about this. Your problem set will also come out of that, the end of that lesson there, so once the video is over, you can actually start working on the problem set. All right, so we're starting with linear equations, something you've seen before, done before. However, this is going to mold into what we'll be looking at the rest of the semester, which is an elementary approach to linear algebra in form of what we call a matrix. We'll talk about that in our next lesson. So let's go ahead and dive into this. Again, this is going to be kind of what I would do in class, probably a little bit more disheveled, but this is what it would look like. All right, so let's take a look at a linear equation to start off with. What is a linear equation? Yes, I apologize for the pixels. But a linear equation is an equation of the form a sub 1 x sub 1 plus a sub 2 x sub 2 plus dot 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 all the way up to a sub n x sub n equals some value of b. Let's talk about linear equations for a little bit. You guys have experienced linear equations. As you can see, this is a linear equation that has an n number of variables to it. We have x sub 1, x sub 2, all the way up to an x sub n. And the a sub 1, a sub 2, all the way up to a sub n are the coefficients of each of those. Notice there's no exponents, no powers to anything higher than 1. It's only 1. And then we've got this equal b, and b could be any sort of constant represented in there, any sort of expression. And you guys also know that a solution to a linear equation are those values that we can plug in for x sub 1, x sub 2, all the way up to x sub n, such that it satisfies the equation. Remember, that's what we like to say. Satisfies is just a way to say that the expression on the left will equal the expression on the right, that it will hold the equation to be true. Let's talk about, though, a system of linear equations. Okay, a system. A system really is a set of linear equations. So we collect all these linear equations, put them together, and we form a system. And as we see here in the diagram, we've got an example of a linear system in front of us. We do have to change our subscripts, though, because for my first linear equation, it was a sub 1, but now I'm going to make it a sub 1, 1, meaning it's the first coefficient of our first variable in our first linear equation. All right. So we have a sub 1, a sub 1, 1, a sub x plus a sub 1, 2. Notice because a sub 1, it's the first linear equation, but it's the second coefficient, and that's because it's part of the second variable x sub 2, all the way up to a sub 1 a sub 1 n, right? A sub 1 n, which is the nth coefficient of our first equation, all the way up to because it's the nth variable, and we have b sub 1. And we can list this out, and you notice then we use some other subscripts down at the very bottom, because I can keep adding as many systems as I want to this set. And I have a sub m1, which means this is the mth linear equation. So we have m linear equations here with n unknowns. Okay, so m linear equations with n unknowns, and this is an example of a linear system. Now you'll see that just for some safe measure, or for some just kind of some shortcuts, I'm going to be writing linear system as just ls. Okay, l dot s dot. So you'll see whenever I see that, even though I wrote it as ls, I will pronounce it as linear system or linear systems, depending on if it's plural or not. And what we're finding with linear systems, several things that you guys are familiar with. We can find a solution to a linear system. This is what we're looking at down below. A solution to a linear system is, again, of values of all of our unknowns such that they satisfy each of our linear equations in this system. So they have to make sure they satisfy each and every single one of them. A couple of vocabulary words that you'll see as you're checking out the textbook is that a linear system can be one of two things. It could be what we call inconsistent or consistent. An inconsistent linear equation or linear system means it has no solution, which means there is not a set of values that can be plugged in for each of the unknowns to satisfy each of them. So that's what we would call an inconsistent system. Or a linear system can be consistent if it does have a solution. One very simple linear system would be to let all of the b values be equal to 0. Whenever we have that, what we call this system is called a homogeneous system. We'll be talking about homogeneous versus non-homogeneous systems, linear systems later on. When I was in college, we had a professor who would call these homogeneous professors, homogeneous. That's how we pronounced them. And so I always, whenever I talk about them, I always tend to say homogeneous, and I pronounce it like him. So if I say that, just remember it's homogeneous or versus non-homogeneous. Also to note that every system that is homogeneous does have what we call a trivial solution, and that trivial solution is to then just let all of our unknowns be 0. Okay, set it equal to 0, and then this would satisfy our homogeneous system because it has, when we let all the b values be 0, there's always then one trivial solution to it, and that is the when all of our x value, or all of our unknowns are equal to 0. All right. However, you could have homogeneous systems which have a non-trivial solution, and we'll talk about those throughout the year. Let's talk about equivalency within our systems. Two linear systems, and so you notice I did L.S.S, so it's plural linear systems. Two linear systems are equivalent if they have exactly the same solutions. So if you take a look at these two systems down here, I've got the first one on the left, x minus 3x, x sub 1 minus 3x sub 2 equals -7, 2x sub 1 plus x sub 2 equals 7. That actually has a solution to it. X sub 1 equals 2 and x sub 2 equals 3. And then the system on the right, 8x sub 1 minus 3x sub 2 equals 7, and 10x sub 1 minus 2x sub 2 equals 14. Those same solutions satisfy that one, which means these two systems are equivalent. What we're going to be learning this first lesson is how to manipulate or transform a linear system into an equivalent, simpler linear system. That way we can solve the linear systems easier for ourselves. And how we're going to be going about doing that is through our process of elimination. So we're going to be using a method for solving a linear system called elimination. Elimination is going to be that form that actually the method transforms a linear system into an equivalent, simpler linear system example. So if you take a look down here, we got an example of a linear system on the left, and let's just on the right. These two actually are equivalent linear systems. Okay, these are equivalent. And what I've done is the one on the left was I used the process of elimination to first remove the value of variable of x from two of the equations, and then remove the variable y from a third equation. And by doing that, then we get this the system such that I already know my solution for z, which then what I can do is called back substitution. I can substitute backward then that z in here, which will then give me my y value, and then back substitute my z and my y into my first to get my x value, so I can use back substitution. And these two systems have the exact same solution, which makes them equivalent. But it's simpler to solve the one on the right because I already know what my z value is, and that's why elimination will help us. And so you'll see an example later on. I'll actually perform elimination. You can see it, and then just that's what your assignment is going to be, is basically talking about elimination and some of the vocabulary throughout the chapter. So anyway, there's a lesson. The solutions to this system is x equals 1, y equals -2, and z equals 3. And again, our process of elimination is going to help us get to a simpler system so that we can actually find the solution faster. Okay, if we are dealing with a linear system of two space, meaning that our linear system can produce lines in a plane, we're encountering, you guys have seen this before, we'll encounter three types of solutions with these. We'll encounter where our two or more lines will intersect at a given point, which means there is a unique solution to the system, which means there's one and only one set of unknowns that satisfy each of the equations. We'll have a set of lines that have no solution, which means actually they are provably then parallel. We'll find that they are parallel lines in the plane. Or we'll have infinitely many, which means both equations actually produce the exact same line. So they intersect everywhere, which then means they're infinitely many. And you guys have seen this before way back in Algebra 1 days. There are also solutions to 3-space. So let's imagine then we have planes, right? When we see a linear equation of x plus 2y plus 3z equals 6, that's a plane. We've talked about planes back last semester. Those who are new to us, though, that does represent a simple plane, a simple surface of a plane. And if we have 3 of those, then we can imagine what happens is those 3 planes are interacting within the space, 3-space. So when the 3 planes intersect at precisely one point, they share one point in common with all. We call that a unique solution, and we can find that happen in some cases. We can also find that there are infinitely many solutions where the planes actually have an intersecting line. Where they intersect, there is a line that's formed that produces infinitely many solutions that can happen with all 3 planes, or there are in fact no solutions. In this example, it shows that there are 2 planes that are parallel. It's not always the case that the planes have to be there has to be a pair of parallel. There are some cases in which all 3 planes just simply aren't parallel, yet do not all intersect to form a line, or do not intersect to form a single solution, a single point, which means again you'll find no solution in that case. So you see, kind of envisioning our 3-space with those simple planes and seeing what type of solutions can unfold with our planes interacting in 3-space. All right, so the last several examples here we're going to do is just simply solve our systems. And we're going to be using the process of elimination, and you'll see this is, in fact, dead simple. What I did first was to use elimination. I'm going to take my first equation and leave it alone. But what I'm going to do is I'm going to use process of elimination. I'm going to either, in some cases, I need to multiply a given equation by a certain scalar, and then add it to another equation. When I do that, it's going to, what I'm trying to do is eliminate one of the variables in that sum, right, as I add the equations together. And so what I did first was I realized that my first and second equation, they both have opposite coefficients of my x value. So I'm going to just take my first equation, and I'm simply just going to add it to my second equation. So I just add my first equation to my second equation, and I produce a new equation that has eliminated the x value, because x plus negative x is going to get rid of that, and then simply then I'm left with the remaining sum of my other variables. So I'm going to add my negative 2y to my positive 3y, and I simply just get y. I do my 3z minus plus my negative 1z gives me a positive 2z, and then I do 9 plus this negative 6 gives me a positive 3. All right, so I'm going to do this again. I'm going to actually try to produce another equation, and again I'm going to try to eliminate the x value. So I can produce another equation that uses y and z, and then I can have a smaller system and use elimination on the smaller system to then find out what my missing value of z is first, what I'll do. What I did next was I actually used my second equation and my third equation, and I noticed that if I multiplied my second equation by 2 and then added it to my third equation, it would also eliminate that value of x. You never want to use the same 2 equations twice, right? I've already used 1 and 2. Now I'm not going to use 1 and 2 again. I could use 1 and 3. I can use 2 and 3. Those are my other options. I've already used 1 and 2, so I can't use 1 and 2. I'm going to use, in this case, I use 2 and 3. I could do 1 and 3 if I wanted to, and get another system that contains y and z, but I noticed how it's going to be simple just to multiply my second equation by 2, and then just add it to my third equation. So multiply by 2 in the middle equation there. And you guys can do some mental math with me. So negative 2x plus 2x cancels that out. I get 6y because I doubled that. Add that to negative 5. It gives me a positive y. Double z there. So I get negative 1z. Add that to 5z. I get then a positive 3z. Doubled negative 6. I get negative 12. Add that to 17. I get 5. Okay, so there's my now new equation that I got from, so this top one, again, came from these two, and then this bottom one here came from these two. Again, I compare 2 equations together just to eliminate one of the variables. Now I have a smaller system of just y and z, and I'm going to eliminate y in this case. Very simply, what I did was I multiplied the top equation by a negative 1, and then added it to my bottom equation. So multiply the top equation by negative 1, and then add it to my bottom one. So I get negative y plus y, it cancels out, that's 0. I get negative 2z plus z, z gives me a positive z. And then -3 plus 5 gives me a positive 2. So there's my value of z, right? Which, in fact, this is part of my linear system. What I've really done is what I can do is I can pick. So each one of these has an equation to it, and I basically pick one equation out of each of these, right? Pick one equation out of here, one equation out of here, one equation out of here, put them together, and I can form an equivalent linear system. So if I pick the top equation out of each of them and then put them together, this is an equivalent linear system because they have the exact same solution. So as you see earlier, we saw earlier that whenever I use a process of elimination, it does make my system much easier to solve, right? We call this, and this is kind of future text, we call this upper triangular. We see that it kind of forms this upper triangular little thing here going on. Anyway, to solve the rest of the way, I back substitute z in. When we do this, I get y equals -1, and then I back substitute y and z in to my first equation. That was bad. And I get x equals +1, and then I pair that with my z, which was 2, and there we have it. There's my solution to the system. Very, very simple. Okay, and our TI-9s can actually solve systems like this very quickly. Very, very quickly, in fact, and I can show you guys how to do that when we get back to the classroom, and I get everybody a TI-89. Let's do another one. Let's take a look at this guy here. Notice that we actually have, this is an, remember how it works? There are m equations of n unknowns. This is actually 3 equations of 2 unknowns. 3 equations of 2 unknowns. For this one, what we're going to find is when we begin eliminating, we're actually going to find our value of y very quickly. But since we have all 3, remember, to find a solution, we have to find a value of x and y that satisfy all 3 of our equations. Where I began was actually with my top 2 equations. And what I did was I was beginning to eliminate the value of x. So I multiplied the top equation by -3 and then added it to my second equation. So I multiplied the top equation by -3 and added in. My x values are gone, but for my y value, -5 times -3 is +15. Add 15 to 2y, we get 17y. Do 6 times -3 is -18. Add that to 1, it gives me -17. Oops. Let me erase that. We get -17. Solve for y, divide by 17 on both sides. We get y equals -1. So we know what our y value has to be. Let's then, what we're going to have to do is we want to make sure we can actually get the same x value. Because if I plug -1 in for y, then I should get the same x value for all 3, and this would then give me my proper solution to my equation. So let's plug, basically what I'm going to do is I take my top equation, x minus 5, and I times y, but I've plugged -1 in there. So solve for x, you get x equals 1. Okay, let's do our middle equation there, plug -1 in, which we should expect it to satisfy that one. So we plug -1 in for that, and we get 3x plus 2 times -1 equals 1. And again, it satisfies, we get x equals 1. But for the last one here, take a look. If I plug -1 in for the last one, we do not get the same x value. We have 5x plus 2 times -1 equals 1. Solving for x, we get 3/5. All right, so this does not work. What we try to do is we found a y value, an x value that actually satisfies the first, but it doesn't satisfy the third. And then what we'll find is no matter what we do, if I were to pair up these middle 2 and try to solve for y, or these top 2 and try to solve for y, what we'll find is that nothing will work. So there is no value of x and y that will satisfy all 3, which means we have a case of no solution. This would be if we were to actually graph these 3 lines. We will actually find that they will not all intersect at any one given point. Essentially, the lines are non-concurrent. They will intersect each other, yes, but there is no one point of concurrency of all 3. That's a no solution for this example. One last example we're going to look at here. Let's do it once more. This is actually 2 linear equations of 3 variables. 2 linear equations of 3 variables. So we're going to solve for x, y, and z in this case. And what I did first was I took my top equation, I eliminated x. So I multiplied by -2, everything by -2, and then added it to the bottom one. So multiply the top one by -2 with me, do some mental math, and add it to the bottom one. That cancels out my x values. -2y plus 3y gives me a positive y. -2 times -2 is a positive 4. Add that to 4z gives me an 8z. And then multiply negative or 5 by -2 gives me a -10. Add that to 2, that gives me a -8. So anyway, there's my elimination of x value. And you'll notice then I can't do this again to get another system, to get another equation only in y and z. So what I'm going to do is just temporarily leave it like this. Sorry, what I'm going to do is what I'm gonna do is I'm gonna do actually solve. No, let's do this. I'm gonna leave it like this. I'll come back to it in just a second. What I'm gonna do is now I'm going to go back to my original 2. In this case, instead of eliminating x, next time I'm gonna eliminate y. So let's eliminate y in this case. And to eliminate y, what I'm gonna do is just multiply everything by -3, and then add that to my next one. So multiply everything by -3 in my top equation, add that to my bottom equation. So -3x plus 2x gives me a -x. -3y plus positive 3y cancels out. 6z plus 4z gives me a 10z, positive 10z. And then I get a -15 plus 2 gives me a -13. Now you'll notice again, these two right here, they do have something in common. Both of these equations are actually have z in common. So what I can do with the top one is I can re-express this in terms of then z. So I'm going to do y equals, and I've basically solve for y, so get y by itself, -8z minus 8. And then what I can do is, then as my bottom one here, I can solve for x. So if I get x by itself, let me rewrite that x here. Get x by itself. I solve for x, I would get then 10z plus 13. Okay, 10z plus 13 as I solve for x. Now what you're noticing then is this has infinitely many solutions because both my x and y are actually dependent on the z value. So how would I then, so I know this actually has infinitely many. There is no one best solution to this. That means that all solutions will work and there's not one that is better than the others. But how would I present this solution? I would actually present it this way. The best way to present this would be to actually write x equals and then 10z plus 13. Hold on, let me fix that 13. Y equals -8z minus 8. Man, I'm really bad at writing. And then z equals, and I can just say all reals. So basically, z can be anything. Pick z to be anything, and then I can plug that value in for my x and y. Now, another way to present this is I could parameterize this, meaning pick a value to parameterize each of these. So I can say let z equal t, which then means y would equal -8t minus 8, and then x would equal 10t plus 13. So I could parameterize this as well as a way to present my solution. So pick a value of t, that's going to give me my z, y, and x values respectively. As a solution. All right, so that concludes our lesson for 1.1. It's a very simple introduction to our elementary linear algebra system. So please be working on the problem set. You're going to hop over to Canvas, open up the 1.1 homework assignment, and you'll find the problems that I've picked out of the section for you to work on. One last little note that I will make a comment about with homework assignments. You will need to inject intuition and some creativity in some of the problems that you encounter in the problem set that I have picked. So this is not necessarily a rote mathematics. You're going to learn that there are some remember, mathematics is more than just numbers and calculations and methods. It's also this process of creativity and logic that you will have to inject into your solutions as well. All right, if you guys have any questions, make sure you email me back with that. Be good and do good.